Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the oldest and deepest questions ever asked. What actually are space and time? Before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these calm explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own small corner of the universe. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey together. You can rest your mind here. There will be no math to solve, no equations to chase, only the slow unravelling of an idea. Because space and time are not just numbers and coordinates. They are the invisible rhythm beneath every heartbeat, the stage upon which every star, thought and memory exists. And though they seem so familiar, the truth is, no one truly knows what they are. We only know how they behave and how we feel them passing. So, take a slow breath, and let's begin with that feeling, the stillness before motion, the quiet before time begins to flow. Imagine the night before the world begins to move. You're lying on your back, eyes closed, listening to the faint pulse of your own heartbeat. Nothing seems to change, yet everything is already in motion. Blood, atoms, the distant earth turning beneath you. This is where our story begins, in the strange silence between movement and awareness. Before we could measure time, we could only feel it. Long before science, before clocks or calendars, people measured the passing of time with their senses. The rising sun, the swelling moon, the slow return of the seasons. A mother knew time by the growth of her child. A farmer knew it by the soil's patience. The earliest calendars weren't carved in stone. They were written in memory, in rhythm, in breath. Time wasn't something counted, it was something lived. And space was not yet the cold black void we imagine today. To the ancients, it was the sky that breathed above them, the distance between mountains, the expanse between two hands reaching out. It was a wordless sense of place, of belonging somewhere instead of nowhere. Space and time were not separate things. They were experiences, a feeling of change and position, of where and when we happen to exist. Philosophers would later give those feelings names. Plato imagined that reality was only a reflection of perfect unseen forms, a higher geometry beyond the reach of touch. To him, space was not empty but full of invisible order, a kind of cosmic architecture. Aristotle disagreed. He believed that emptiness could not exist at all, that nature filled every void, that there was always something, never nothing. Between these ideas, a question formed that would echo through millennia. Is space a real thing that exists on its own, or merely the distance between other things? Leibniz thought of space and time as relationships, not entities. They were the web connecting events, not the frame containing them. If nothing existed, he said, there would be no space or time at all because there would be nothing to relate. But Newton, living in the age of clocks and telescopes, saw things differently. To him, time flowed like a great river, steady and absolute, whether or not anything drifted upon it. Space was the vast stage upon which the universe unfolded. Everything else, the planets, the stars, the people, were just actors within it. It's easy to see why Newton's vision caught on. The world around us feels like that kind of stage. You drop a cup, it falls. The stars move across the sky, not because the sky bends, but because we do. Even our language obeys this intuition. We speak of spending time as if it were a currency, of losing time as if it could be misplaced. We say time moves forward, though no one has ever seen it walk. But deep down we sense that this picture isn't complete. When you close your eyes and listen to your heartbeat, you're not measuring anything, you're inhabiting a moment. That moment isn't a dot on a timeline, it's a presence, something living and elastic. We feel time not as a number but as motion, as the difference between what was and what is now. Perhaps that's why every culture, from the Greeks to the Egyptians to the Maya, turned to cycles, the seasons, the stars, the pulse of the moon, to make sense of existence. Time to them was not a line stretching endlessly ahead. It was a wheel, turning. In that ancient sense, time had no beginning or end. It was simply the rhythm of the universe breathing. The Babylonians tracked it through eclipses, the Chinese through the dance of the planets, the Mayans through calendars as intricate as poetry. Each was trying to understand the same mystery, how change could happen inside something that never truly changes. And so, humanity's earliest science was not about what time is, but what it does. It flows, it returns, it carries. We were the first witnesses of motion, not in the stars, but in ourselves. If you think about it, your very body keeps time. Your heart beats around 70 times a minute. Your breathing drifts between 10 and 20 cycles. Cells divide, grow old, and renew, all to their own quiet rhythm. Even sleep follows its own internal tide. The rhythm of life itself may be our first clock, the whisper of time made flesh. When you lie awake at night, noticing that seconds stretch longer than they do by day, you're not wrong. Time feels slower when the world grows still. That's your mind's clock shifting gears, measuring less by motion and more by awareness. In a way, we each live in our own private universe of time, stretching and compressing moments as our attention flickers. Before Einstein or Newton, before equations or pendulums, this was how we knew time. Not by number, but by change. Not by distance, but by feeling. Space was the breath between things. Time, the echo between heartbeats. The stars above us, the ground beneath us, even our thoughts moving from one to the next, each is a kind of motion. And maybe that's what space and time have always been. Motion, seen from different directions. Somewhere, long after these early philosophers, a young man sitting under a quiet sky would start to wonder what motion truly meant. Why light always moved at the same pace. Why time seemed to slow for those in flight. He didn't yet know it, but his questions would bend both space and time forever. Imagine standing beneath a sky untouched by city lights. Above you, the stars hang still, not as holes in darkness, but as distant fires caught in a great still breath. For the early thinkers, this night sky was more than beauty. It was a question. What is the space between the stars made of? Is it nothing? Or is it something invisible holding everything in place? Plato imagined that beyond the changing world we see, there exists a perfect order, an unseen geometry. What we touch and see are only shadows of that perfection. Space, in his view, was not empty but filled with harmony, like a song whose notes we could never quite hear. For him, to measure the universe was not to count distances, but to seek the pattern that gave rise to everything. The stars were not floating in nothing, they were embedded in meaning. Aristotle, however, looked at that same sky and refused to believe in emptiness. He argued that nature cannot stand a void. If there were truly nothing between objects, how could motion even happen? What could things move through? He imagined the universe as a set of concentric spheres, crystal layers surrounding the Earth, each carrying planets like jewels. To move was to push against the surrounding substance, the cosmic air that filled everything. To Aristotle, the universe was full, never hollow, never silent. Centuries later, the debate would rise again. The philosopher Leibniz proposed that space and time are not things at all, but relationships between events. There is no space where nothing happens, only the distances and intervals between things that do. He imagined a universe where meaning arises from relation. If all matter vanished, space and time would vanish too because they would have nothing left to connect. Newton, the mathematician of motion, disagreed. To him, space and time existed even if nothing else did. They were the grand stage upon which matter moved, the eternal background that never changed. Whether the planets danced or stood still, the cosmic theatre remained. It was a bold, beautiful vision, a universe of absolute stability, where the laws of motion were written once and for all. The contrast between them is subtle but profound. Leibniz's universe was like a conversation, real only when someone spoke. Newton's was like an empty room waiting for voices, and though Newton's idea would shape the next 3 centuries of physics, the whisper of Leibniz's thought would never quite fade. As human instruments grew more precise, so too did our picture of space. Astronomers built telescopes that pierced deeper into the heavens. Navigators used the stars to cross oceans, trusting that celestial positions were steady, absolute. Clocks began to measure the pulse of time more faithfully than any heartbeat. Sand glasses, pendulums, and eventually the ticking of gears brought time down from the stars and placed it on the mantelpiece. For the first time, humans could point to a dial and say, "This is when." Ships departed by the clock, empires scheduled by the hour. The rhythm of civilization began to align with mechanical motion, and time became something you could buy, lose, or waste. The ancient cycles, the moon, the harvest, the seasons, were replaced by the steady march of seconds and minutes. The universe itself seemed to beat like a perfect clock, and humans saw themselves as gears within it. Still, the mystery remained. The more precisely we measured space and time, the less we understood what they truly were. Was time flowing through space? Was space the container for time? Were they separate at all? By the 17th century, new instruments had found something astonishing. Light did not behave like sound. It did not need air to travel through. It moved as though the void itself could carry it. But that made no sense. How could nothingness transmit motion? So scientists imagined an invisible ocean filling all of space, the luminiferous ether. They pictured the planets drifting through this unseen sea, their motions stirring invisible waves. For a while, it seemed elegant, almost poetic, a cosmic ocean of light. But even as they wrote those equations, a quiet unease grew. The ether could never be seen, never tested, and if everything moved through it, what would it mean to be at rest? The deeper they searched for the ether, the less it appeared to exist. They were chasing something that vanished the closer they looked, an echo of Aristotle's full universe fading into Newton's empty one. The tension between fullness and emptiness, between relationship and container, became the heartbeat of physics. If space was truly empty, how could it carry light? If time was universal, why did it flow differently for each observer? No one could yet know that a young man working in a patent office in Bern would one day resolve these questions, not by filling the void, but by reshaping it. But before Einstein could arrive, humanity needed to imagine something else. The universe as a system of motion so perfect, so mathematically clean, that even God would admire its clockwork. This was the dream of Newton's age, a dream of order carved into infinity. As the Enlightenment dawned, time was no longer divine or mysterious. It was measurable. The heavens became predictable. Comets returned on schedule. Tides obeyed calculation. The great cosmic ballet seemed fully understood. The only mystery left was why it worked so perfectly. And yet, deep down, the philosophers still felt uneasy. If the universe was only motion in empty space, where did meaning come from? If time was just the ticking of cosmic gears, why did we feel its flow so personally, its joy, its loss, its weight? The questions never truly disappeared. They only grew quieter, waiting. Perhaps space was not empty after all. Perhaps time was not a current, but a sensation. a pattern our minds trace to make sense of change. Long before Einstein's equations, this suspicion had already begun to shimmer beneath the surface of thought. Something about the void still felt alive. If you close your eyes now and imagine that sky again, no stars, no sound, only the deep black stillness, you might begin to feel what those early thinkers felt, the almost sacred tension between nothing and everything, between being and not being, between a cosmos that holds you and one that leaves you floating in the dark. It is that tension that carried us forward, from philosophy to physics, from imagination to observation. And in the next part of our quiet journey, the sky itself will begin to move, the apple will fall, the planets will dance, and time, for the first time, will find a rhythm that can be measured. The story of space and time begins to change under a grey English sky. In the late 1600s, a quiet man named Isaac Newton was watching the world with an eye for patterns. He saw the same forces in a falling apple and in the orbit of the moon. In that single thought, he brought the heavens and the earth into one law. The legend of the apple is often told as a moment of sudden revelation, but it was not the apple that mattered. It was the question it left behind. Why does anything fall? What pulls the moon into its curve around us? Newton imagined an invisible thread that stretched from the earth to the apple, from the sun to the planets. He called that thread gravity. Not a push, not a touch, but a pull acting across empty space. He gave the universe new rules. Motion continues unless disturbed. Every action meets an equal reaction, and the force of attraction between two objects grows weaker with distance but never vanishes completely. These were the first universal laws of motion, laws that worked as well for a tossed pebble as for the moon itself. The same equations could describe a cannonball and a comet. What he created was more than mathematics. It was a vision of a perfectly balanced universe, every movement predictable, every orbit traceable, as if creation itself were a grand machine wound by a steady hand. Time, in Newton's cosmos, flowed evenly everywhere, like a great clock whose pendulum never faltered. The phrase he used was absolute time, an ever-flowing river that moved the same for all things, regardless of where they were or how they moved. It was a comforting idea. It meant that if you knew the starting position and motion of every object in the universe, you could, in principle, predict the future and retell the past. The entire cosmos became a symphony of moving parts, each obeying the same rhythm. Humans had, for the first time, a sense that the universe could be understood completely by reason. Imagine it, a vast celestial clock ticking steadily, planets swinging like gears, moons spinning like jeweled wheels, gravity as the thread that keeps it all connected. The heavens were no longer the domain of gods, they were a mechanism. Newton had turned the divine into the measurable. He also introduced a constant of gravity, an unseen strength that determined how strongly two masses attract each other. Though written as a symbol in his equations, it represented something elegant and invisible, the weight of connection itself. But Newton's world wasn't all cold precision. He saw beauty in its order. He described the universe as a grand design set into motion by a creator who rarely needed to intervene. In his view, the cosmos ran so perfectly that even the divine could rest. It was the ultimate reassurance. The laws of the universe were knowable, and within them lay peace. Still, not everyone felt so certain. The philosopher Leibniz argued again that Newton's absolute space and time were illusions. He said that what truly mattered were the relationships, how one thing moved relative to another, not against some invisible backdrop. If you could erase all the stars and planets, what would space even mean? Could there be time without anything changing? For centuries, Newton's answer dominated. It worked. Ships navigated by his equations. Engineers built bridges and cathedrals using his laws. Astronomers predicted eclipses centuries in advance. The precision of his mechanics became the rhythm of the industrial age. Steam engines puffed along to the same metronome that swung the planets. The gears of factories mirrored the gears of the heavens. For a while, the world truly did feel like a clock. You could hear it in the click of pocket watches, see it in the rise and fall of pistons, the steady beat of machines. Every tick was a tiny echo of the universe itself. Even language began to change. People spoke of mechanisms of thought, of calculating the world, as if existence itself were a kind of elegant arithmetic. But there was something hidden in the perfection. Newton's equations assumed that time flowed at the same rate everywhere. A second on Earth was the same as a second on the Moon. A minute in motion was the same as a minute at rest. It made the math clean, but it ignored what the human heart already knew. The time feels different when you're waiting, or when you're falling, or when you're afraid. The clock ticks, but the moment stretches or shrinks depending on how we live it. Of course, Newton couldn't have known that the universe itself shared that secret, that time really could stretch and shrink, not only in the mind but in the stars. For his age, the mechanical universe was enough. It gave people a sense of mastery, of knowing their place in a grand, reliable order. Even chaos could be explained. The apple would fall, the tides would turn, and all of it could be traced with ink and compass on a page. Still, there were hints that the clock might not be wound as tightly as it seemed. Astronomers noticed tiny discrepancies in the orbits of planets, especially Mercury, whose path around the Sun didn't fit perfectly with Newton's calculations. They assumed another planet must be disturbing it, a hidden world called Vulcan, never found. And then there was light itself, so strange, so constant. When scientists measured its speed, they found it never changed, no matter how they moved. That was impossible in Newton's world, where motion should always add or subtract. It was as though light refused to obey the universe's most sacred rule. The stage of absolute space and the river of absolute time had begun to crack, even if no one yet knew it. Something deeper was waiting to be discovered. Something that would show that space and time were not the stage at all, but part of the play. Still, for the generations who lived under Newton's sky, the world felt understandable, predictable, a divine machine turning gently through eternity. Humanity had, for the first time, turned mystery into mechanism. It was the age of certainty, and the ticking clock was its lullaby. If you close your eyes, you can almost hear it. The slow, patient rhythm of a perfect universe, each motion following another, all of it held together by invisible threads. For centuries we believed that was the whole story. But the smallest glimmer of doubt was already shining on the horizon. A young mind, restless and curious, was beginning to question whether time itself could bend. Imagine for a moment that the universe really is a grand clock. Its gears are the planets, its pendulum is the sun, and its ticking, the steady heartbeat of existence, is time itself. That was the world Isaac Newton gave us. A cosmos where everything, from the fall of an apple to the sweep of a comet's tail, could be traced through invisible geometry. It was the age when time was believed to move like an arrow, straight and constant, never bending, never hesitating. To live in such a universe was strangely reassuring. You could look at the stars and believe they obeyed the same rhythm as your pulse. A second for you was a second for the moon, for Jupiter, for the farthest star. It didn't matter where you were or how you moved. Time flowed evenly everywhere, like the perfect ticking of a clock that filled the whole of space. Newton had given the cosmos a single rhythm, one tempo for all existence. If the universe is a stage, then Newton's time was the music of that stage, universal, steady, and eternal. Everything danced to it, and it cared nothing for who or what was moving. A planet could race around the sun, a candle could flicker, or a heart could stop beating, time itself would never change pace. It was the one thing that seemed immune to change. This idea of absolute time found its way into more than science. It crept into our language, our culture, our sense of control. We began to speak of saving time as though it were money. We said we spend it, waste it, lose it. But in Newton's world, time couldn't be lost or wasted. It simply was. It flowed like a river that never ran dry, carrying everything along with it. Even when humans built clocks to measure it, those clocks weren't creating time. They were merely marking the flow of something that already existed, as if the tick of a pendulum were an echo of the cosmic pulse itself. The mathematics behind it all was beautifully simple. To calculate a planet's position, you only needed to know its velocity, its mass, and the force pulling on it. From that, you could predict its path forever. You could even imagine rewinding it, running time backward like a film, and every object would return to its original place. The equations made no distinction between past and future. It meant that, in theory, if someone were powerful enough to know every detail of every atom, they could foresee every moment of the future and recall every instant of the past. This vision of total predictability came to be called determinism. It was a comforting dream for scientists and a quietly terrifying one for philosophers. If every motion of every star could be foreseen, then what of human choice? Were we just small mechanisms within a larger mechanism, turning without knowing why? Most people didn't mind the implication. The Newtonian universe was orderly, sensible, and stable. The heavens obeyed it. The tides obeyed it. Life itself seemed to obey it. And for a time, that was enough. But slowly, small cracks began to appear in this perfect clockwork. The first came from light. It behaved in ways no one expected. It could reflect like a ball, yet also spread like ripples in a pond. Some experiments suggested it travelled through an invisible medium, the ether, that filled all of space. Others hinted that perhaps there was no such medium at all. When physicists tried to measure the Earth's motion through this supposed ether, they found, astonishingly, nothing. Light always moved at the same speed, whether you chased it or ran from it. It was as if light refused to obey the rules of motion that everything else followed. If light's speed was constant, it meant that something else had to give, either space or time, or both. But in Newton's universe, that was unthinkable. Space and time were the scaffolding of reality itself, fixed and eternal. To question them was to question the foundation of everything. Still, not everyone could ignore what they saw. A few scientists began to suspect that the universe was not as absolute as Newton imagined. But the idea of giving up universal time was almost heresy. After all, if time didn't flow the same everywhere, what did it even mean to say that two events happened at once? In Newton's world, simultaneity, the sense that two things could occur at the same moment, was simple. You could strike a bell in London and another in Paris, and if you heard them ring together, you knew they were simultaneous, but light travels with a delay. What if the signals took different times to reach you? What if now in Paris wasn't quite the same now in London? The thought was too strange to consider seriously, and yet, nature has a quiet way of revealing her secrets when we least expect it. The late 19th century saw the first clues of what was to come. Experiments with electric fields, moving magnets, and beams of light hinted that space and time might not be as rigid as they seemed. But the equations were messy, and few understood them. The universe continued to tick as before, or so it appeared. To ordinary life, Newton's time felt perfectly true. The clocks in train stations, the schedules of factories, the orbits of planets, all moved in predictable harmony. Even today, much of our daily world still runs on Newton's rhythm. Planes fly, bridges hold, and the moon rises exactly when predicted, because for most things his laws are close enough to perfect. But if you could look deeper, past the gears of the clock, past the calm face of time itself, you'd find that its evenness is an illusion. Somewhere beneath that steady rhythm, space and time are quietly changing shape. Time, it turns out, is not the same for everyone. The river that Newton thought was universal has hidden currents, flowing slower or faster depending on how you move or how close you are to something massive. This truth would not fully surface until the early 1900s, when a young man with wild hair and gentle eyes began to ask what it would feel like to chase a beam of light. His name was Albert Einstein, and he would take Newton's clockwork and melt it into something alive. In his hands, time would become elastic, space would bend, and gravity itself would be reborn as geometry. But before that revelation could unfold, humanity first had to let go of its most comforting illusion, the idea that time was absolute, that 1 second could belong equally to all. Because once you see that every clock in the universe keeps its own rhythm, you can never look at time or space the same way again. At the turn of the 20th century, the world was humming with invention. Trains stitched cities. Together, telegraph wires carried voices faster than ever before, and humanity had begun to dream of flight. Yet, beneath all that progress, a quiet puzzle lingered. Something small and stubborn that refused to fit the grand Newtonian machine. Light. No matter how scientists measured it, light always travelled at the same speed. Whether the Earth was moving toward a distant star or away from it, whether a lantern was waved or still, the beams of light never wavered in their pace. It was as though the universe had chosen one unshakable rhythm and refused to budge. The instruments were precise, the experiments repeated again and again, but the answer was always the same. The speed of light did not change. This seemed impossible. According to Newton's laws, if you ran towards something, you should reach it faster. If you moved away, slower. But light ignored that logic completely. It was immune to the usual rules of addition and subtraction. Something about it defied the very structure of space and time. In 1905, in a small patent office in Bern, a 26-year-old clerk named Albert Einstein sat at his desk, reviewing diagrams for electrical devices. He was not a university professor, he had no laboratory, but in his spare hours he let his mind wander into thought experiments that stretched the limits of imagination. He liked to picture himself chasing a beam of light through the air. What would he see if he could catch up? Would the beam freeze before his eyes like a glowing thread, or would the very idea of catching it make no sense at all? That question became the seed of one of the most revolutionary ideas in history. Einstein began by asking something deceptively simple. What if the speed of a light was constant not just for some observers, but for all of them? What if it never changed, no matter how you moved? To make that possible, something else had to bend. Either the way we measure space, or the way we measure time. He proposed that the laws of physics must look the same for all observers moving at constant speeds, and that the speed of light in a vacuum is the same for everyone, everywhere. Those two principles, gentle as they sound, turned reality upside down. The result became known as special relativity, a name that hides just how strange it really is. If light speed stays fixed, then space and time can no longer remain separate. They must shift together, like dancers keeping perfect balance. When one stretches, the other contracts. Imagine two friends, Alice and Ben. Alice stays on Earth while Ben takes a spaceship moving close to the speed of light. To Alice, Ben's clock ticks slower. His heart beats more gently. His entire sense of time drawn out like soft taffy. From Ben's perspective, though, everything feels normal. It's Alice's world that rushes ahead. Each of them believes their own time to be true, and both are right. This effect, called time dilation, isn't just theory. It's been measured again and again. Tiny particles created high in the atmosphere, called muons, live longer when moving fast than when still. Atomic clocks flown on airplanes tick just slightly slower than those left on the ground. Even the navigation satellites orbiting Earth must correct for this difference, or your phone's map would drift miles from where you stand. The universe quietly adjusts every second, every signal, to keep harmony across its shifting frames of reference. But time isn't the only thing that bends. When objects move near light speed, their length along the direction of motion seems to shrink. This is known as length contraction. It's not that they're physically crushed, but that the fabric of space itself rearranges to preserve the constancy of light's motion. Distance, once thought to be absolute, becomes as fluid as time. Then there's simultaneity, the idea that two events happening at the same moment might not be truly simultaneous for everyone. Imagine a train speeding along the tracks. A bolt of lightning strikes each end at the same instant, at least from the perspective of someone standing on the platform. But for a passenger on the train, one flash will always come first. The moving observer and the still observer inhabit different timelines, stitched into the same reality. From these gentle but radical ideas, a new picture of the universe emerged. Space and time were no longer separate ingredients, but a single, woven fabric. Spacetime. To move through space was to move through time, and vice versa. The two could not be pulled apart. Einstein's realization also led to one of the most famous equations in history, which he expressed softly as energy equals mass multiplied by the square of the speed of light. It means that matter and energy are not distinct substances, but different expressions of the same underlying thing. A tiny bit of mass can unfold into an immense amount of energy, like a drop of water revealing the strength of an ocean. This connection, simple in form but infinite in meaning, later explained why stars shine, how the sun burns, and how the universe itself transforms matter into light and light into matter. The heart of every star is Einstein's idea in motion, turning mass into radiant fire. What makes this story so beautiful is that Einstein didn't start with mathematics. He started with empathy, the ability to imagine what the world might look like from another point of view. His universe was not fixed but relational. Time and space depended on where you stood, how you moved, and how you observed. Reality was no longer a stage, it was a conversation. Yet the most poetic part of all is this. Even though everything else changes, distances, durations, simultaneity, the speed of light remains constant, a kind of cosmic heartbeat pulsing steadily through all of creation. It is as if the universe keeps its own secret measure of time, and everything else must dance to its rhythm. For the first time, humanity understood that the cosmos is not absolute but elastic. Time can stretch, space can bend, energy can turn into matter and back again. The laws of motion still hold, but they are deeper and more mysterious than anyone had dreamed. Einstein's insight didn't destroy Newton's universe, it completed it. Newton had shown us how objects move through space. Einstein showed us that space itself moves with them. The clock still ticks, but now its hands are drawn on soft fabric that can twist and curve. If you listen carefully, you can almost hear that cosmic clock breathing, its rhythm expanding and contracting with every heartbeat of light. It's no longer the rigid tick of machinery, but the living pulse of space-time itself. Einstein's revolution didn't end with light. Once he had pulled time and space together into a single fabric, the next question followed naturally. If motion can stretch and bend that fabric, could gravity do the same? And if so, what exactly is gravity? In Newton's universe, gravity was a force, an invisible hand pulling one mass toward another. You drop a stone, it falls. Planets circle the sun because of that same pull, bound like marbles in invisible strings. But to Einstein, the idea of a mysterious force acting across empty space felt incomplete. What if, instead of a force, gravity was a kind of geometry, a natural result of the shape of space and time themselves? he began to imagine space and time not as a stage, but as a flexible fabric that could stretch, ripple, and curve. Massive objects like stars and planets didn't simply sit in that fabric, they deformed it. The sun, for example, didn't tug on the Earth in some invisible way. Instead, it created a dimple in the fabric of space-time, and Earth simply followed the curve of that distortion, much like a marble rolling around the dip of a stretched sheet. It was a breathtaking shift in perspective. There was no pull at all, only motion along curves in a landscape that was itself dynamic. Matter told space how to curve, and curved space told matter how to move. Einstein expressed this relationship in a set of equations so elegant that even other scientists called them beautiful. But those symbols, dense and precise, can be translated softly. They say that the presence of mass or energy changes the geometry of the universe around it, and that geometry in turn dictates how everything else moves. You, me, the moon, and even beams of light all follow the bends of this cosmic fabric. This means that when you feel your body pressing into your chair, what you're actually feeling is space-time pushing back, your body following the natural curve of Earth's presence. You're falling constantly toward the planet's centre, but the floor interrupts your motion, keeping you suspended in place. Even when you stand still, you're caught in an ongoing conversation with the geometry beneath you. One of the first proofs of Einstein's new vision came from starlight itself. He predicted that light passing near a massive body would not travel in a straight line but would bend around it, following the curve of space-time. During a solar eclipse in 1919, astronomers observed exactly that. The apparent position of distant stars shifted slightly as their light grazed the sun's edge. The results made headlines around the world. Overnight, Einstein became the face of a new universe, one that shimmered and swayed like a great breathing fabric. The idea that light could bend under gravity also meant that time itself must slow near massive bodies. Clocks tick more slowly in stronger gravitational fields. You experience this every day, though the difference is unimaginably small. Your head, being farther from Earth's centre than your feet, experiences time moving ever so slightly faster. It's only a fraction of a second, but it is measurable. This gentle stretching and compressing of time has become one of the most precisely confirmed effects in all of physics. You can think of it like this: space tells light how to move, and time tells matter how to rest. Together they weave a conversation so seamless that we only notice it when something extraordinary happens, like a black hole, where gravity becomes so intense that the fabric folds in on itself, creating a place where even light cannot escape. In those regions, time nearly stops, and the geometry of space-time collapses into mystery. Yet, despite its strangeness, Einstein's theory explains the ordinary world perfectly. It tells us why GPS satellites orbiting Earth must adjust their clocks to stay accurate. High above the planet, time moves just a little faster than it does on the ground, and without correction, our navigation systems would drift by kilometers every day. Einstein's equations quietly keep your phone's map aligned, your airplane on course, and your morning commute grounded in reality. His insight also redefined energy. The phrase, energy equals mass multiplied by the square of the speed of light, wasn't merely a curiosity. It was a doorway into understanding how matter and energy shape the fabric of existence. Because mass and energy are two forms of the same thing, anything that carries energy, even light, can curve space-time. The universe itself becomes self-aware, responding to its own contents, shaping itself with every pulse of radiation, every heartbeat, every flicker of heat. The implications were staggering. Space was no longer the backdrop of the story. It was one of the characters, living, responsive, and endlessly evolving. The Earth didn't orbit the Sun because of a pull. It surfed along a gentle curve in space-time's flow. The Moon's motion wasn't commanded by gravity. It was a quiet dance written into the geometry of the cosmos. To visualize it, Imagine a vast field of soft fabric stretching in every direction. Place a heavy sphere at the center, the sun, and watch how the fabric dips around it. Smaller spheres, planets, roll along those curves, not because they're dragged, but because the fabric guides them. This is how Einstein's universe works. No invisible forces, just the shape of the stage itself. At first, many scientists resisted this idea. It was too abstract, too poetic, almost mystical. But as evidence grew, light bending, clocks slowing, planets moving exactly as predicted, the truth became impossible to deny. The cosmos truly was curved. Einstein's theory of general relativity, published in 1915, replaced Newton's invisible strings with geometry itself. It revealed that the universe is not mechanical but dynamic, a living tapestry that stretches and ripples under the weight of energy and time. And though the equations are complex, the heart of the idea is profoundly simple. Everything affects everything else. The stars bend the fabric that shapes your path. And in turn, you, with your small mass and energy, bend it too, even if by an immeasurable amount. Einstein's curved universe also planted the seeds of new questions. If space could stretch locally around planets and stars, could it stretch everywhere at once? Could the entire cosmos itself expand? And if it could, what would that mean for time? These quiet questions would soon lead to the discovery that the universe is not static, but growing. An idea that would change our sense of place forever. For now, though, it's enough to rest on this realization. Gravity is not a force tugging on you from afar. It's the shape of the world beneath your feet, the bend in the path that light takes from a distant star, the gentle curve of time itself flowing around your heartbeat. You're not standing in space, you're standing on it, woven into the same fabric that carries galaxies and dreams alike. When you picture an astronaut drifting through orbit, it's easy to imagine them as floating, free from gravity's touch. They glide in silence, a silver silhouette against the curve of the Earth, as if the pull of the planet has finally let them go. But the truth is more curious and more beautiful. Astronauts are not weightless because gravity is gone. They are weightless because gravity never stops. They are, in a sense, always falling. Orbit is not the absence of gravity, it is its perfect balance. The spacecraft and everything inside it is constantly being pulled toward Earth, but it is also moving forward so fast that its path curves at exactly the same rate as the planet's surface below. Each second, it falls and misses the ground. That endless fall is what keeps it circling. The moon does the same around the Earth, and the Earth around the sun. Everything that moves through space is caught in this graceful fall, woven into the quiet geometry of gravity. From this view, even standing still is a kind of motion. The floor beneath your feet holds you in place only because it pushes back against your natural tendency to fall toward the planet's center. You're not apart from gravity, you're participating in it. Every object, from a dropped pebble to an orbiting satellite, is following the same instruction written into the fabric of spacetime: follow the curve. When Einstein proposed that gravity wasn't a force but the shape of space and time themselves, this idea took on new clarity. If you could see spacetime around Earth, you'd see a smooth depression, like a soft indentation on an infinite sheet. The astronaut isn't floating above that dip, they're gliding along its walls, forever circling the gentle curve of Earth's influence. It's less like flying, and more like being carried by a current you can't feel, yet which shapes your every motion. This invisible curvature leaves tiny fingerprints everywhere. The clocks aboard satellites tick just slightly faster than those on Earth's surface, because time itself moves differently at altitude. Up there, farther from the planet's centre of gravity, space-time is stretched a little wider. A second in orbit passes more quickly than a second on the ground. Down here, close to the Earth's mass, time runs a little slower, its rhythm pulled by gravity's gentle hand. It's not just theory, it's practical, measurable, and absolutely vital. The satellites that help you navigate your day, those quiet travellers forming the global positioning system, depend on this correction. Each one carries an atomic clock so precise it can lose only a billionth of a second in an entire day. Yet even that is enough to throw off your position by kilometres if relativity isn't accounted for. So, engineers adjust those clocks, tuning them to run slightly slower before launch. Once in orbit, freed from Earth's deeper gravity well, they fall into rhythm with time's natural stretch. Every time your phone locates you, it's performing a little symphony of relativity, harmonizing ground and sky. The bending of time isn't limited to satellites. On Earth, atomic clock experiments have confirmed it again and again. Set two identical clocks side by side, leave one on the ground and lift the other just a few meters higher. After some time, the elevated clock will have ticked a fraction of a second faster. It's imperceptible to us, but perfectly visible to physics. A quiet proof that even height can change the tempo of time. We see gravity's fingerprints in other ways too. The light from distant galaxies arrives stretched, its colour shifted toward the red end of the spectrum. This gravitational redshift is light losing a little energy as it climbs out of a deep gravitational well. Like a note from a violin that deepens as it drifts through fog, the light slows its rhythm as it escapes the grip of a massive star or black hole. High above us, cosmic particles called muons, born from the impact of starlight on our atmosphere, live longer than they should. Moving at near the speed of light, they experience time more slowly, just as Einstein predicted. By the time they reach the surface, their internal clocks have lagged enough for them to survive the journey. In their fleeting lives, they've confirmed something profound. Time itself bends to motion and gravity alike. Everywhere we look, from the orbiting satellites to the faint glow of galaxies, the same story unfolds. Gravity is not a chain, but a whisper. It curves space, it slows time, and it keeps everything in gentle conversation. What we call falling is really the universe's natural motion, a return to the shape it prefers. Even you, sitting or lying still, are falling, not just toward Earth, but through space-time. You're moving forward in time at the speed of a light, carried by the universe's geometry. To live is to fall gently along that invisible slope, always moving, always part of the curve. When astronauts float in orbit, they sometimes describe a strange feeling of timelessness, as though day and night lose their meaning. They circle the Earth 16 times a day, seeing sunrise and sunset again and again, until those words stop making sense. Their internal clocks, their bodies, their very cells must adapt to a rhythm that isn't natural, yet it's a reminder that natural is only what feels normal from here, on this patch of gravity. Time, in truth, is elastic. It stretches, compresses, and adjusts, always relative to where you stand and how fast you move. If you could see the flow of space-time with your eyes, you'd see waves rippling through it, small vibrations caused by the motion of massive bodies. We've only recently learned to detect them. In 2015, scientists recorded these ripples, gravitational waves, for the first time, born from the collision of two black holes a billion light-years away. When they reached Earth, they had stretched and squeezed our planet by less than the width of an atom. Yet that whisper from across the universe confirmed that space-time is not static. It trembles, hums, and remembers. From the curve beneath your feet to the distant waves rolling through the cosmos, gravity is everywhere, shaping every moment you experience. It keeps the moon from drifting, holds the oceans in rhythm, and stretches the light from ancient stars. It slows your heartbeat by a fraction of a second each century. It gives structure to everything, yet remains unseen. And so, when you gaze at the night sky, you're not looking into emptiness. You're looking into a vast curved ocean, an ocean that holds you as much as you hold it. Every star, every orbit, every fall is part of one continuous motion through this cosmic fabric. Gravity doesn't just pull, it connects. It links your breath to the earth, your seconds to the stars. It is the silent geometry of being. And as that geometry unfolds across the heavens, it leads us gently to the next question. If the curve of space-time shapes everything around us, could that same fabric be changing on the grandest scale of all? Perhaps the universe itself is stretching, not in its contents, but in its very foundation, the fabric of space expanding like a slow, eternal breath. If gravity bends the space around a planet or a star, what happens when we step back and look at everything at once? The entire sky, the web of galaxies stretching out to infinity. For centuries, people imagined that the universe was fixed, like a grand cathedral made of stars. The heavens turned, but the structure itself did not. Einstein, too, at first believed the cosmos must be static. His equations for general relativity suggested that space could stretch or shrink, yet he added a balancing term, a kind of mathematical handbrake, to keep the universe still. It would take others to show that the cosmos was not a sculpture, but a dance. In the early 20th century, a Russian mathematician named Alexander Friedman began to explore what would happen if that handbrake were released. He found that Einstein's equations didn't prefer stillness at all. The natural state of the universe was motion. Space could expand, and with it, the distances between galaxies would grow. Around the same time, an American astronomer named Edwin Hubble was pointing a massive telescope toward distant clusters of light. What he saw matched Friedman's predictions perfectly. Every galaxy was moving away from us, and the farther it was, the faster it receded. The universe wasn't just drifting, it was swelling. To imagine this, think of a loaf of raisin bread rising in an oven. The raisins don't move through the dough itself stretches, and every raisin sees every other one moving away. In the same way, galaxies aren't flying through space, they're carried apart as space itself expands. There is no center, no edge. Every point stretches from every other, quietly, evenly, like a slow breath that began long before we arrived to notice it. This discovery changed everything. It meant the cosmos had a past, a moment when all the galaxies were closer together, when the universe itself was denser, hotter, more compact. It meant there might have been a beginning, a time before time, when all of space was contained in a single bright whisper. The expansion also suggested a future, a fate determined by the delicate balance between gravity's pull and the outward rush of the fabric itself. But the expansion brings with it a subtle mystery. In Newton's world, energy could neither be created nor destroyed. It only changed form, kinetic into heat, potential into motion. Yet in an expanding universe, the very idea of conservation grows fuzzy. When light travels through stretching space, its waves lengthen, losing energy to a process that has no name in classical physics. It's not that energy disappears, it's that the concept itself becomes blurred, because the container of reality is changing size. Space is doing work. The universe isn't a closed box, it's an instrument still tuning itself. We can see the result of that tuning in the cosmic microwave background, the faint afterglow of the early universe that still hums softly across all directions. It's the residual warmth of creation, stretched by billions of years of expansion, until it now appears as a chill radio whisper, barely above absolute zero. When you tune an old television and see static, a tiny fraction of that snow is ancient light, older than the stars, echoing across time to remind us that everything once fit inside a single moment. Even today, expansion continues, and not just at a steady pace, it's speeding up. The galaxies aren't only drifting apart, they're accelerating. Something unseen is pushing them outward, overcoming the pull of gravity. Scientists call it dark energy, not because it is dark, but because it remains unknown. It fills the universe like an invisible pressure, a whisper from the vacuum itself urging everything apart. Some think it is a property of space, others a hidden field of energy woven into the cosmos. Whatever it is, it has been gently reshaping the fate of everything for billions of years. To feel what this means, picture yourself holding a balloon. On its surface, dots mark galaxies. As you blow air inside, the surface expands, and every dot moves away from every other. There is no special center on the balloon's skin. The expansion happens everywhere at once. From any galaxy's point of view, it would seem as though all the others are fleeing from it. That's how the universe appears to us. We're not at the center, but we can't help feeling as though everything moves away. It's not that we're being abandoned, it's that the space between us is growing. This also gives rise to a natural boundary, a horizon we can never cross. Because space expands, light from very distant galaxies may never reach us. Those worlds are moving away faster than light can bridge the gap. It's not that they're breaking a speed limit. The road itself is stretching beneath them. Beyond that cosmic horizon lies a silence we can never touch. The more the universe expands, the smaller our observable island becomes. Yet there is something comforting in that limitation. The horizon defines our portion of the sky, our pocket of the infinite. Everything we can ever observe fits within a sphere about 90 billion light-years across. A vast bubble of perception floating in an ocean of unknowable space. We are stitched to that bubble by light itself, each photon a messenger from some faraway dawn. When we look out, we're also looking back in time. The light from the Andromeda galaxy left when early humans hadn't yet stood upright. The light from quasars billions of light-years away began its journey before the Earth was even born. Each glimmer is a page in the story of expansion, written in the language of time. If you could speed up the universe's history, you would see galaxies receding like embers from a dying fire, their colours reddening as their light stretches through space. The farther they drift, the slower their glow, until they fade beyond sight. In that distant future, the sky may grow emptier. The galaxies that fill our telescopes today will one day slip beyond the cosmic horizon, leaving only the faint light of our local cluster, a small, quiet corner of what was once a crowded, shining cosmos. Still, there is no need for sadness in that image. Expansion is not destruction, it is transformation. The fabric of space continues to weave itself, creating new distances, new rhythms, to new forms of stillness. The universe breathes, and we, existing within it, are part of that breath. Every inhale, every exhale, mirrors the slow rise of galaxies and the fading echo of their light. Perhaps even time itself expands as space does. The seconds stretch with the cosmos, their edges softening, their flow growing quieter. The same geometry that guides planets and curves starlight now shapes the future, pulling it gently forward. So when you gaze up and feel the distance between stars, remember that what you see isn't emptiness, it's motion. The universe is growing, not into anything, but within itself. And though that expansion may one day carry all things beyond one another's reach, in this moment, under this sky, we are still connected by the same fabric, still part of the same unfolding breath. If the universe began as a moment of unimaginable order, a single spark where everything was compressed and smooth, then what has happened since is the slow blooming of chaos. The stars, the galaxies, the warmth and light that make our nights shimmer, all of it is part of a long story written by disorder. And yet, that same disorder gives us the illusion of time flowing, of life moving forward instead of standing still. Imagine a cup of warm tea left on a table. Slowly it cools, sharing its heat with the air. The molecules dance more lazily until both the cup and the room reach the same temperature. That's entropy. the universe's tendency to spread energy out, to mix things together until they can no longer be unmixed. It's why spilled milk never jumps back into its glass, why footprints fade from the sand, why stars eventually burn out. It's not malice or decay, it's simply the natural direction of change. Physicists call it the arrow of time. It points toward increasing entropy, toward the mingling and blending of all things. In the grand equations of physics, there's no real reason why time should move forward instead of backward. The laws work both ways, like a mirror reflecting a perfect symmetry. But entropy breaks that symmetry. It gives time a preference, a sense of direction. It's the one part of nature that cares about before and after. If you could see the universe's timeline as a film reel, every frame would exist at once, past, present and future laid out side by side. In that picture, nothing truly happens. All moments simply are. But entropy gives us the experience of moving through those frames, one after another. It makes the film play. Without it, there would be no flow, no memory, no story, only an endless still image of everything that ever was or will be. Think of an egg cracking into a bowl. Physics doesn't forbid the opposite, that the yolk and shell could suddenly leap back together, but the odds are so tiny that it might as well be impossible. There are infinitely more ways for the universe to be messy than for it to be neat. Entropy is simply counting possibilities, and it finds far more ways to scatter than to gather. Order is a rare exception, chaos is the rule. But from this quiet chaos, beauty emerges. Stars ignite because gravity resists entropy, pulling matter inward until heat and light push back. Life exists because energy flows from concentrated sources, the sun, food, warmth toward cooler surroundings. Every breath you take is an act of entropy, energy moving from order to disorder in exchange for the spark of life. The same principle that makes tea cool also makes hearts beat and minds think. The universe's decline into disorder is paradoxically the reason we are here to notice it. There is something gentle in this realization. We are creatures of imbalance, living in the narrow space where energy still flows, where gradients still exist. The warmth of the sun, the chill of night, the difference between what is and what was, those differences are what make the world alive. When they fade, when everything reaches equilibrium, time as we know it will end. Not because clocks will stop, but because there will be nothing left to change. You can see entropy everywhere once you start looking. In a melting ice cube, in the fading echo of a song, in the wrinkling of skin. It is the quiet, patient artist behind aging, weather, and memory. It erases edges and blends boundaries. It makes room for impermanence, but it also writes the music of time, the steady one-way rhythm that carries us from past to future. Even the cosmic expansion we spoke of before is an expression of entropy. The universe began smooth and hot, and over billions of years, it has cooled and clumped into galaxies and stars. As it expands, it continues to lose its initial order. Energy thins out, temperatures drop, structures slowly unravel. One day, far in the future, the last star will burn its final hydrogen atom and darkness will spread. The universe will reach a state called thermal equilibrium, where everything is the same temperature everywhere, a stillness beyond imagining. It will be, in a sense, timeless. Yet we shouldn't think of entropy as destruction. It's the quiet balancing of opposites. For something new to form, something else must disperse. When a tree grows, sunlight's concentrated energy is spread out. When you fall in love, the chemistry in your brain burns a little more fuel, mixing energy into warmth and feeling. Disorder is the cost of existence, the soft heartbeat beneath every moment of creation. And though the arrow of time feels universal, it's local too. Inside a hurricane, chaos increases, but in the core of a forming star, gravity fights back, creating pockets of structure and light. Entropy rises overall, but within it, patterns bloom. It's as if the universe balances its urge to scatter with an equally persistent tendency to create islands of meaning, small places where order briefly holds, where life can wonder at its own fragility. There's a quiet comfort in knowing that even as the cosmos moves toward disorder, every act of warmth, every flicker of motion, every word spoken into the air contributes to the grand tapestry of change. We are part of entropy's story, not victims of it. Without the flow of energy from order to chaos, there would be no music, no sunsets, no laughter. The universe's gradual fading is not an ending, it's a lullaby. And when you think of time, think of it not as a river that drags us forward, but as the slow diffusion of everything that ever was into everything that will be. The present moment is just the point where order and disorder meet, briefly, before continuing their dance. If you leave that same cup of tea overnight, by morning it will be cold, indistinguishable from the air around it. The heat will have vanished, though not really gone, just spread, shared. In that sharing lies the universe's deepest truth. Nothing is lost, only rearranged. Entropy isn't the enemy of time, it's what allows time to exist at all. So perhaps we can think of time's arrow not as something pushing us forward, but as something unfolding, a grand exhale of the cosmos. Every second that passes is space expanding, energy dispersing, and existence redistributing itself in endless combinations. And somewhere within that spreading warmth and cooling light, a small planet glows faintly with life, an island of temporary order floating in a sea of beautiful disorder. You've probably noticed how strange time feels. Hours can vanish in an instant when you're lost in a conversation, yet seconds stretch endlessly when you're waiting for something that matters. Time bends not just near black holes or speeding clocks, but inside your mind every single day. It flows faster, slower, even seems to stop, all depending on where your attention rests. If physics gives us the structure of time, the brain gives us its texture. Inside your skull, millions of tiny neurons hum in patterns of electrical fire, weaving the present moment out of memory and expectation. To your brain, the now isn't a single point. It's a short stretch of awareness, perhaps a few seconds long, stitched together into what feels like a continuous flow. The scientist David Eagleman once described it as the window of the present, always sliding forward, refreshed each moment by perception and recall. In that sense, the present is not something we stand in. It's something our minds build for us. The brain doesn't experience time directly. It gathers sights, sounds, and sensations, then arranges them into order. There's always a slight delay, a fraction of a second between what happens and when you feel it. Yet you never notice that gap, because your mind is constantly blending the past into the present, smoothing the edges so the world feels seamless. Deep inside your brain lies the hippocampus, a structure no larger than your thumb. It acts as a kind of librarian for your experiences, storing and replaying fragments of memory. It's this part of you that creates continuity, the gentle thread that links who you were yesterday with who you are now. Without it, life would be a scatter of moments, unconnected and fleeting, like stars with no constellations between them. When you recall an old memory, the hippocampus lights up again, replaying the pattern of neurons that once fired during the original experience. In that instant, your mind doesn't just remember, it re-enters the past. You're not looking back through time, you're standing in it, briefly, before being pulled forward again. The past, in that sense, isn't gone. It's a quiet echo your mind can still awaken. This is why time feels so personal. We don't experience it as equations or coordinates, but as emotion, as longing, anticipation, nostalgia, and hope. A moment can feel endless not because physics has slowed, but because consciousness has deepened. Pain stretches time. Joy makes it vanish. A heartbeat shared can hold an eternity. A sleepless night can feel like forever. Scientists studying time perception have found that our brains are poor clocks. They don't measure seconds precisely, they estimate them. When something captures our attention fully, we store more sensory detail, and afterward, that memory feels longer. When we're distracted or bored, the record is thin, so time feels short. This is why the first time you visit a new place, the day seems long and rich, yet the second visit feels faster. Your brain isn't marking minutes, it's counting novelty. In moments of danger, the system changes again. The brain floods itself with stress hormones and your internal clock begins to run in overdrive. Every detail sharpens, the world seems to slow down. You catch the glint of a car's mirror, the texture of your own breath, the sound of your pulse. Later, when the danger has passed, you remember those moments as if they lasted far longer than they did. But they didn't. It was you who sped up, your awareness unfolding in higher resolution, capturing more frames per second of experience. Dreams too play with time. You might wake from a dream that feels like it lasted for hours, yet only minutes have passed. In sleep, your brain stops receiving the usual flow of information and begins to invent its own. Freed from the constraints of the physical world, it weaves time from imagination alone. That is why dream time can stretch, loop, or collapse entirely. In those hours of quiet night, you're living in a private universe where time is pliable, molded by thought rather than gravity. Perhaps that's what consciousness truly is, a soft bending of time. We don't perceive every event equally. We highlight, skip, repeat. We linger in certain moments and rush through others. Our awareness paints motion onto still frames, turning a series of frozen instants into the story of a life. This is not so different from the way the universe works. Relativity tells us that all moments, past, present, and future, coexist. The block universe, as philosophers call it, contains every second that has ever been or will be. But within that vast stillness, entropy gives us motion, and consciousness gives us perspective. Together they create the illusion of time flowing forward. We are like readers moving across the pages of a book that has already been written, and yet there's a quiet beauty in that illusion. Without it, we couldn't feel growth, change, or meaning. Memory would have no sweetness, anticipation no thrill. The illusion is the very thing that allows love, regret, and wonder to exist. Maybe the universe doesn't need time to unfold, but we do. It's how we measure living. Some philosophers have suggested that consciousness and time might even be the same phenomenon. The brain's act of organizing experience gives birth to the feeling of duration. Without memory, there is no past. Without attention, there is no present. What we call time could simply be awareness taking shape. The physicist Carlo Rovelli once wrote, "We are time, we are its memory." And maybe that's the most human truth of all. Each of us carries a small fragment of the universe's sense of time, a private clock made not of gears or light, but of memories. When we look back on our lives, we don't see equations, we see stories. A handful of moments, vivid and fleeting, arranged by emotion into meaning. So, when you think of time passing, remember that it's not something happening outside you. It's happening through you. Every laugh, every glance, every pause becomes a stitch in your own personal space-time, your unique geometry of being. Close your eyes and recall a memory from long ago. The smell of rain, the sound of a friend's voice, the flicker of light through a window. For a brief moment, you're there again. The present dissolves into the past, and yet you are still the same observer travelling through the story. Perhaps this is what gives time its gentleness, its ability to hold both loss and presence at once. It doesn't erase, it rearranges, it doesn't vanish, it lingers. In that sense, the flow of time is both illusion and truth. The illusion is motion, the truth is change. and consciousness is where the two meet, softly, like the edge between night and dawn. If our minds can bend time this easily, then what of the universe itself? What if space and time are not fixed at all, but emerge from deeper patterns, connections so small, so subtle, that they weave the fabric of reality beneath everything we know? The next step of our journey drifts quietly in that direction, toward the smallest scales imaginable, where the boundary between matter, energy, and information begins to dissolve. The deeper we look into reality, the more it begins to shimmer, as if everything solid is only an illusion held together by motion. Down at the smallest scales of nature, the neat geometry of Einstein's spacetime starts to fray. The world becomes fuzzy, restless, uncertain. It's as though the universe itself whispers, "You cannot draw a perfect line here. You cannot know both where and when precisely." At human scale, space feels continuous. You can stretch your hand forward, trace a curve, or measure a distance with a ruler, and it all seems smooth. But deep beneath that smoothness, far beyond atoms, far beyond even their nuclei, lies a frontier where the familiar rules dissolve. This is the realm of the quantum, where particles blink in and out of existence and probabilities replace certainty. Here, even time seems to flicker, appearing not as a flowing river, but as discrete ripples in an unseen pond. The first clues of this strange world came from light itself. At times, light behaved like a wave, spreading, interfering, blending. But in other experiments it acted as if it were made of individual packets of energy, which scientists began to call quanta. Later, these quanta would be known as photons. The revelation was unsettling. Reality could not decide whether it was continuous or made of pieces. It was both, depending on how we looked. This dual nature soon spread to matter. Electrons, the tiny companions that orbit atomic nuclei, also behaved like waves. Their position was no longer fixed. It could only be described by a cloud of possibilities, a pattern of chance. You could predict where an electron was likely to be, but never exactly where it was until you looked. The moment of observation itself seemed to decide the outcome, as if the universe was waiting for attention before revealing its shape. Then came a man named Paul Dirac, who tried to weave quantum mechanics together with Einstein's special relativity. The two theories described very different worlds, one smooth and fast-moving, the other jittery and uncertain. Dirac's unification gave birth to something astonishing, the prediction of antimatter. For every particle of matter he found, there should exist a mirror version with opposite charge, like a reflection that could annihilate its twin in a flash of energy. The universe, it seemed, was built not only from presence but from balance. But Dirac's equations, though elegant, still couldn't capture gravity. The very thing that curved space-time refused to fit inside the quantum puzzle. It was as though nature kept its two most powerful ideas, relativity and quantum mechanics, on opposite sides of a glass wall. Each could describe its own realm perfectly, yet when combined, the mathematics shattered. Something was missing. Scientists began to wonder whether space and time themselves might break apart at the tiniest scales. Perhaps they weren't continuous at all, but built from discrete building blocks, tiny units smaller than anything we can imagine. This boundary is called the Planck scale, named after Max Planck, the father of quantum theory. It's so small that if an atom were the size of our solar system, a single Planck length would still be smaller than a grain of sand. At that scale, space-time might not be a smooth sheet, but a woven fabric of microscopic threads, a network of quantum connections vibrating endlessly. Out of that idea grew theories like loop quantum gravity, which suggests that space itself is made of loops, tiny knots of geometry. Imagine zooming in on emptiness and discovering it isn't empty at all, but made of countless, interlocking rings of energy. These loops twist together, forming what we perceive as space, the very act of distance. The idea that one thing can be separate from another might arise from how these loops intertwine. Another vision, string theory, takes the concept further. It imagines that everything, from electrons to galaxies, is composed not of particles, but of minuscule strings vibrating at different frequencies. The vibration determines what kind of particle you perceive. One vibration gives you an electron, another gives you a photon. The entire universe becomes a cosmic symphony, each note resonating through many dimensions. Space and time in this picture are not the stage, they are part of the music. It's a strange thought, that the solidity of your hand or the weight of a mountain could come from the rhythm of invisible strings, flickering so quickly that the mind cannot follow. Yet this idea may not be so foreign. You already live in a world made of frequencies. Every colour you see, every sound you hear, every warmth you feel is a vibration. The universe is a concert and matter is the melody. Still, even these elegant ideas don't fully solve the puzzle. At scales where quantum effects meet gravity, space-time becomes unpredictable. It bubbles with energy, like water just before boiling. Tiny black holes flicker in and out of existence. Time might pause, reverse, or branch. In these extremes, distance loses its meaning. You can no longer say where one thing ends and another begins, because everything is entangled, woven together by invisible threads of information. Physicists describe this restless region as the quantum foam. It's not a foam of matter, but of geometry itself. Even here and there become uncertain, smeared across probabilities. It is within this foam that the seed of everything we know may have formed. The expansion of the universe, the arrow of time, the birth of space itself. It's tempting to imagine that if we could peer close enough, we might see the very code of the cosmos written not in equations but in patterns, loops, vibrations, connections. But perhaps the truth is subtler. Maybe reality is like a painting viewed from too close. The closer we get, the more the smooth image breaks into points of colour. Yet step back, and the illusion of continuity returns, complete and calm. That's what space-time might be, a masterpiece that seems seamless from afar but is made of countless quantum brushstrokes underneath. Even the idea of nothing begins to change here. What we call empty space is not truly empty. It seethes with fluctuations, particles that appear and disappear so quickly that they can barely be said to exist at all. This restless vacuum is what allows light to travel, forces to act, and atoms to form. The void, it turns out, is alive. All of this leads to an unsettling but graceful thought. Perhaps the universe is not built from things at all, but from relationships, from vibrations, connections, and patterns of information. Matter, energy, space, and time could be secondary. Emerging from deeper harmony we have yet to understand. If space-time truly unravels into something smaller and stranger, it may not be chaos that waits beneath, but music, the quiet hum of the quantum world composing the fabric of everything. If everything around us, every atom, every beam of light, every breath, is woven from vibrating threads and quantum loops, then perhaps space itself is not something that exists on its own, but something that emerges from relationships, a pattern, not a thing. A web of connections rather than a container. That idea, radical as it sounds, is beginning to reshape how we think about reality. It suggests that space and time may be byproducts of information, the way knowledge about the universe arranges itself. Imagine the cosmos as a vast library, every grain of energy a page, every interaction a sentence. Each bit of matter carries information about everything it touches. When two particles meet and interact, they exchange not just energy, but a trace of each other's presence, as if whispering, "I was here." The sum of all those whispers becomes the geometry of the universe. Space, in this vision, is not the stage where information exists, it is the information written in a language we're only beginning to decipher. The clue that led scientists toward this idea came from an unexpected source: black holes. These cosmic abysses seem to erase everything that falls into them, hiding matter and light behind an event horizon from which nothing can escape. Yet, according to the laws of quantum mechanics, information can never truly be lost. It can change, scatter, or hide, but it cannot vanish completely. How then, scientists wondered, could a black hole destroy the information about what it swallowed? In the 1970s, the physicist Jacob Bekenstein proposed that the information inside a black hole must somehow be stored on its surface, not its interior. Later, Stephen Hawking's work on radiation confirmed the idea. The amount of information a black hole can contain, its entropy, is proportional not to its volume, but to the area of its event horizon. In other words, the surface, not the space inside, tells the story. Reality, it seemed, might be holographic. The three-dimensional world we experience could be a projection of information, inscribed on a two-dimensional boundary, just as a hologram encodes depth within a flat image. This insight became known as the holographic principle, one of the most poetic ideas in modern physics. It means that our universe could be like the inside of a soap bubble, with all its contents, galaxies, stars, people, and thoughts, emerging from information stored on the bubble's surface. Every point within space would then be a reflection of data woven into that cosmic skin. You're not simply inside the universe. You're part of its information, a living pattern within its code. Later, a discovery called the AD-CFT correspondence gave the idea mathematical weight. It showed that a universe with gravity could be fully described by a simpler system on its boundary, one without gravity at all. In soft terms, it's as if everything happening in 3 dimensions is the shadow of a dance taking place on a flat stage beyond our view. Geometry itself becomes an echo of relationships, a shape sculpted by entanglement. Quantum entanglement is the heart of this story. When 2 particles become entangled, their states remain connected no matter how far apart they drift. Measure one, and the other responds instantly, as if space between them doesn't exist. It's not communication, it's unity. The 2 particles are not separate things, they are parts of a single, larger reality. The more scientists studied this connection, the more it seemed that entanglement might build space itself. The invisible threads that tie particles together could be the true architecture of space-time, stitching proximity and distance out of shared information. To imagine this, think of a vast tapestry where each thread knows how tightly it's woven to every other. The closeness of those threads determines the structure of the fabric. Where the weave is dense, space feels near. Where it's loose, distance grows. If you pluck one thread, the vibration travels through the pattern, carrying information from one region to another. The tapestry is space, and the vibration is gravity, the bending and shifting of relationships across the cosmic web. Some researchers describe gravity not as a fundamental force, but as entropic, meaning it arises from the universe's tendency toward balance in its information. When something moves, or when matter clusters together, the distribution of information changes. Gravity may be the universe's quiet way of restoring equilibrium, space adjusting itself to keep its own memory intact. In that sense, gravity is not a pull, but a correction, the geometry of remembering. The universe, it seems, is built not only on energy but on recollection. This perspective reshapes what we mean by existence. If space is information, then every atom of you is also a message. Your body, your thoughts, your memories are encoded vibrations within the cosmic pattern. And because information can never truly disappear, something of you may always remain, diffused into the universe's memory long after your form is gone. Like music fading into silence but never lost from the score. It's humbling to realize that the emptiness between stars might be less like nothingness and more like a vast ocean of meaning, carrying the record of everything that has ever happened. Even vacuum, that apparent void, hums with activity, particles flickering into being and vanishing again, their brief lives adding threads to the fabric of information. The silence of space is only apparent. Underneath it, a chorus of quantum exchanges never stops singing. If you could listen to that cosmic hum, you might hear not sound but correlation, tiny echoes linking every event to every other. And perhaps that's what we're sensing when we speak of intuition, connection, or déjà vu. Faint glimpses of an underlying unity, reminders that we are patterns inside patterns. As we reach the edge of this idea, one question remains. If information gives rise to space, could time also emerge from it? Could the flow we experience be the universe sorting through its own data, processing events one by one to maintain coherence? Time, then, would be computation, the cosmic mind running its program, line by line, with every second a new update to existence. And yet, even in this digital metaphor, the poetry endures. We are not cold numbers or static code. The information that forms us is dynamic, luminous, ever-changing, like light reflecting on water, never still, never lost. The universe, far from mechanical, becomes a living memory, thinking itself into being. If that's true, then perhaps gravity isn't a force, space isn't a void, and time isn't a river. They're all expressions of one deeper truth, that reality is the act of remembering itself. And in that grand remembrance, every thought, every star, every heartbeat plays its part, a quiet pulse in the eternal network of knowing. If you could step outside of time, truly outside it, and look down at the universe, you might see every moment laid out before you like pages in an open book. The first stars forming, the birth of the Earth, your own heartbeat right now, and whatever lies billions of years ahead, all coexisting in a single, vast pattern. In such a view, before and after lose their meaning. The past doesn't vanish. It simply rests beside the future, waiting to be read. Einstein's equations quietly suggest that such a perspective may not be entirely fantasy. Within the deep mathematics of general relativity are strange, looping paths known as closed time-like curves. In plain language, these are routes through spacetime that could, at least on paper, lead an object back to its own past. Imagine moving forward in time step by step, only to find yourself walking into yesterday. These solutions don't appear in the simple geometry around Earth, but under certain extreme conditions, rotating universes, massive spinning cylinders, or warped regions of space, they emerge naturally. One of the first people to notice this was the mathematician Kurt Gödel, a friend and contemporary of Einstein at Princeton. Gödel was known for his work on logic, the man who proved that no system of rules could ever explain itself completely. Perhaps it was fitting, then, that he discovered something similar in space-time. His solution to Einstein's equations described a universe that rotated as a whole, and within that rotation, time itself folded back on itself like a ribbon. In Gödel's universe, if you travelled far enough, you could return to your own past. A few years later, another physicist, Wilhelm van Stockum, found something similar hidden in the mathematics of a rotating cylinder of dense matter. Space around such an object would twist like the air in a tornado, and within that swirl, paths could loop backward in time. They were elegant, haunting solutions. Theoretical, yes, but not forbidden. If time can loop, then what of cause and effect? Could any event create itself? Could you, by travelling back, prevent your own journey from ever happening? These are the paradoxes that haunt the imagination. The simplest of them, the so-called grandfather paradox, asks, what if someone travelled into the past and prevented their ancestor from living long enough to create them? Who then pulled the trigger? Who vanished first? Physicists, being cautious storytellers, often answer that the universe may allow time travel only under one rule: self-consistency. Every loop, every event must agree with itself. You can go back, perhaps, but you cannot change what already was. You can be part of the story, but not the author who rewrites it. In this view, the past is not fragile. It is firm, elastic perhaps, but unbreakable. Whatever happens in the loop has always happened that way. It's an oddly comforting thought. Instead of the chaos of changing timelines, we get a universe that is self-aware enough to keep its own history tidy. A cosmic editor ensuring the plot never contradicts itself. If you try to stop a chain of events, your very attempt becomes part of the chain. If you throw a stone into a pond, the ripples spread, but they were always part of the pattern written into the water. And yet, even with that rule of self-consistency, there's a lingering mystery. Could time loops exist without being noticed? Could the universe contain small pockets where cause and effect chase each other endlessly, invisible to us? Some theories hint that microscopic versions might occur in the quantum world, where particles borrow energy from the future or echo into the past for fractions of a second before snapping back to the present. It's not the time travel of science fiction, but it may be a quiet truth. Tiny experiments in causality happening billions of times a second inside the atoms that make up our bodies. At larger scales, nature seems reluctant to reveal such loops. The conditions required, a rotating cosmos, infinite cylinders, exotic matter with negative energy, remain speculative, almost poetic. And yet, relativity doesn't forbid them. It simply allows the possibility and then looks away, as if saying, "You may go, but the road will not be easy." Perhaps the universe hides time travel not because it is impossible, but because it is fragile. To make it happen, you would need energies that could tear the fabric of space-time itself. Any disturbance, any small vibration, might unravel the loop. Like a mirage that vanishes when you reach for it, the path collapses the moment you try to walk it. Still, the idea lingers because it touches something human, the longing to revisit moments we've lost. We all carry a quiet wish to return to a certain hour, a conversation we never finished, a sunset that slipped away too soon, a loved one's laugh echoing from years ago. Time travel, at its heart, is not about science. It's about memory, regret, and the tenderness of wanting to hold time still. And in a way, we already do. Every time you remember something vividly, when a scent or a song brings back a forgotten day, you have travelled backward. The memory is not just stored in your brain, it is reconstructed, relived. Your body reacts as if the moment were happening again. The heart quickens, the breath changes. In that small private loop, cause and effect blur. The past returns through you. So maybe the universe doesn't need machines or wormholes to visit the past. Maybe it only needs awareness. Consciousness itself could be the simplest form of time travel, replaying patterns that were once real. Physicists sometimes describe time as a block, where every moment exists simultaneously, already written. But we experience it as motion, page by page, heartbeat by heartbeat. If that's true, then perhaps we're all travellers within the same story, each of us reading our line in the eternal script. In that script, there may be no real paradoxes, only loops of meaning, lives that echo into the future and back again, moments that repeat in new forms. A mother's gesture mirrored in her child, a teacher's words reappearing in a student decades later, kindness rippling across generations. The past doesn't vanish. It reincarnates in the living. So when we ask whether time travel is possible, maybe the gentler question is this: are we not already doing it? Every memory, every inheritance, every pattern passed on is a journey backward. Perhaps the universe never forbade time travel. It simply entrusted it to us in the quietest form possible, remembrance. And if there truly are hidden loops in space-time, maybe they exist not as roads for machines, but as rhythms in existence itself. The seasons turning, hearts beating, stories retold. We loop too, every day, sleep to waking, breath to breath, life to life. The universe might not need to forbid going back because, in its own way, it never stopped. There is a strange kind of silence near the edge of a black hole. A silence not of sound, but of time. From a distance, a black hole looks like a dark sphere suspended in space, its boundary perfectly smooth. Yet this calm hides the most extreme phenomenon in nature, a place where gravity is so strong that even light cannot escape. At that edge, called the event horizon, the rules of time begin to falter. If you were to hover near a black hole, safely, impossibly, just beyond the horizon, you would find your clock running slower than those far away. This isn't just a metaphor. Time itself stretches under the weight of gravity. A second for you could be hours, days, or years for someone watching from afar. From their perspective, you would seem frozen, suspended in place, moving slower and slower until you stopped completely. But from your own view, nothing feels strange. You would still see your seconds tick by normally, still breathe, still think. Time remains faithful to you, even as it betrays the universe outside. This effect, called gravitational time dilation, is one of Einstein's most profound insights. The stronger the gravity, the slower the flow of time. You can think of it like a river growing thick near a waterfall, still moving but sluggish, distorted. At the edge of a black hole, the river freezes entirely. Light itself can no longer climb out. From that moment on, whatever falls inside is separated from the rest of reality by more than distance. It is separated by time. The closer you approach, the more the horizon pulls you in, not just through space, but through history. You can never return to where you started, because in that geometry, returning has no meaning. The direction we call forward merges with down, and after becomes inside. It's as though time and space trade places, and movement itself becomes memory. Scientists use a tool called a Penrose diagram to describe this. Instead of coordinates and numbers, imagine a map of fate, lines showing how light, matter, and time bend near infinity. In those diagrams, black holes are shaded regions where all paths tilt inward, converging toward a singularity, the core where density and curvature become infinite. But we don't need to say infinite to feel its meaning. It's the place where all measures break, where even the concept of next loses its footing. The singularity is the ultimate boundary of now, and yet, paradoxically, black holes are not just destroyers, they are keepers of information. For decades, physicists thought that anything falling into one was lost forever, erased from the record. But then Stephen Hawking showed that black holes can emit a faint glow, a whisper of energy now known as Hawking radiation. It arises from the quantum vacuum, the endless dance of particle pairs that appear and vanish even in empty space. Near the event horizon, one of these particles can escape while the other falls inward, carrying a little bit of the whole's energy with it. Slowly, over billions of years, the black hole evaporates, shrinking until it fades entirely. In those last moments, the black hole becomes a clock, a cosmic hourglass counting down to its own disappearance. The time it takes depends on its mass. A black hole as large as the Sun would take an unfathomable number of years to evaporate, far longer than the universe has existed. Yet no matter how massive, each one must eventually reach its end. The universe, it seems, allows no eternal prisons. Hawking's discovery created a new mystery. If black holes evaporate, where does the information go? The laws of quantum mechanics insist that information can never truly vanish, only transform. So if a black hole disappears, the details of everything it consumed, stars, planets, Perhaps civilizations must still exist somewhere, encoded in the radiation that escapes. The puzzle is whether the universe remembers completely or only approximately. Is the cosmic story written with permanent ink, or does time occasionally smudge its own pages? One interpretation is that information isn't stored inside the black hole but on its surface, much like the holographic ideas we explored before. The event horizon could be a kind of archive, a thin, glowing boundary where all the data about what fell in is preserved in microscopic ripples. As the black hole evaporates, that information is released bit by bit, whispered back into the universe. In this sense, black holes don't erase, they translate. They turn matter into light, light into memory, and memory into space again. Standing at this boundary between existence and oblivion, we see how fragile now really is. What feels like the present moment depends entirely on where we stand and how gravity bends around us. Near a black hole, the idea of simultaneity, that two events can happen at the same time, completely dissolves. For one observer, a second. For another, an age. There is no single, shared rhythm. Time itself becomes local, intimate, personal. This truth extends beyond black holes. Every star, every planet, every human heart distorts space-time ever so slightly. We all slow time around us by a fraction, even if it's imperceptible. Each of us lives in a slightly different timeline, a private version of now. When you speak to someone, the light from your face takes tiny fractions of a second to reach their eyes, meaning they always see you as you were, not as you are. Every conversation is a dialogue between past and present, a small reminder that perfect simultaneity is an illusion. At the scale of the cosmos, these differences are immense. A star billions of light years away might have died before its light ever reached us. When we look at the night sky, we're not seeing the universe as it is, but as it was, a patchwork of overlapping nows. The sky is a museum of ancient light, every star a message delayed by the fabric of space-time. And so, the boundary of now is not at the edge of a black hole, it's everywhere. Every observer, every being lives within their own expanding bubble of time, shaped by gravity and motion. Our universes overlap but never perfectly align. The present, as comforting as it feels, is only a perspective, a shared illusion we call home. Black holes remind us of that illusion's limits. They are the ultimate mirrors, reflecting the truth that time, at its edges, cannot flow forever. It stretches, slows, and eventually stops. And when it does, what remains is not emptiness, but potential, the silent space where the last echoes of motion prepare to fade. One day, far in the future, the universe will reach that same boundary. The black holes will evaporate, the stars will burn out, and light itself will become rare. But before that final quiet arrives, there will still be one last flicker of brilliance, one last photon escaping the darkness. Its journey will mark the end of the story, the final heartbeat of time. There will come a night when the last star burns out. Not suddenly, not violently, but quietly, its fire fading like the breath of a candle in an empty room. The galaxies that now blaze across the sky will one day dim, their starlight thinning into whispers. It will not be a tragic end, but a gentle one, the natural stilling of a cosmic heartbeat that has pulsed for billions of years. This final chapter of the universe is known as the heat death, though the phrase sounds colder than it truly is. It does not mean freezing, it means completion. It is the point when every gradient has flattened, every difference between hot and cold, bright and dark has evened out. Entropy, the quiet mathematician of time, will have finished its long work. Every spark of energy will be evenly shared. There will be no more imbalance left to drive change. If time is the measure of change, then when change ends, so does time. The universe will not stop suddenly. It will simply slow, like a clock running down. Galaxies will drift farther apart until their light can no longer cross the expanding void. Stars will burn through their fuel, becoming embers, white dwarfs fading to black, neutron stars cooling into silence. Even black holes, those deep wells of gravity, will shrink away through Hawking radiation, one faint particle at a time, until they too vanish. And when the last black hole releases its final whisper of light, a single photon escaping into the darkness, there will be no one left to see it. Yet that light will still travel, carrying with it the memory of all that once was. That photon, that tiny messenger, will be the last echo of motion in a universe grown still. The picture sounds lonely, but there is a quiet grace in it. After all, everything that exists now is a continuation of something older, a flame passed down from the Big Bang, burning ever dimmer but never extinguished. The universe began in light, and it will end in light. The first brightness will circle back to the last, closing the loop. We often imagine the end of all things as an apocalypse, a grand finale, a collapse, a fall. But the truth written by physics is softer. The universe does not die. It unwinds. Energy spreads. Order relaxes into equilibrium. Nothing vanishes. It simply becomes too uniform to notice. It's less an ending than a return to stillness. You can see hints of this fate everywhere, if you know where to look. In the faint glow that still surrounds us, the cosmic microwave background, is the aftertaste of the universe's youth. It's the light from when everything was new, stretched thin by time and distance, still warming our sky with its ancient whisper. That glow is a preview of the future too, for when all things become evenly spread, the universe will once again look like that, featureless, calm, and eternal. Yet even in that stillness, the universe may not be truly silent. Some physicists believe that information, the raw code of existence, can never be lost. Even when energy dissipates and structure dissolves, the pattern of what once existed remains written into the fabric of spacetime, like a watermark pressed into blank paper. Every atom that ever lived, every thought ever thought, might leave behind an echo, not in matter or energy, but in information. In that sense, nothing truly disappears. The universe may forget its shapes, but not its story. The final light will not be an erasure, but an archive, preserving the memory of creation within the very emptiness it leaves behind. Perhaps this is how eternity hides itself, not in endless motion, but in perfect memory. Physicist Carlo Rovelli once wrote, "Time doesn't pass, we do." He meant that time is not a river carrying us forward, but a landscape through which we move. We are the travellers, not the flow. When we speak of time ending, what we really mean is that we will have reached the farthest edge of motion, where there is nothing left to travel through. The stage will remain, but the play will be over. It's worth remembering that every cycle of existence carries its own version of this story. A fire burns until its fuel is gone. A wave rises until gravity calls it home. Even your heartbeat, steady and unending, for decades, will one day fade into silence. But that silence is not absence. It's balance, the perfect equality between opposing forces. If you could stand outside the universe in that far future and look back, you would see not darkness, but completion. Every particle, every spark of heat, perfectly distributed. No edge sharper than another, no motion faster than any other. A cosmic equality so profound that time itself has no foothold. And yet, this future is not tragedy. It's the final symmetry of creation. The Big Bang was the universe's first breath, expanding into difference. The heat death will be its exhale, returning to stillness. Between those two breaths lies everything, every galaxy, every atom, every heartbeat, every moment you have ever known. In that sense, you're part of the universe's long inhale and exhale, its rise and return. The atoms in your body were once forged in stars that burned long ago, and someday they will drift again into new forms. The light that left your eyes tonight might travel forever, part of the same final glow that will outlive everything else. If that seems too vast to grasp, remember that you too have your own heat death in miniature. Every night when you fall asleep, your thoughts slow, your body cools, and your mind drifts toward equilibrium. Each dreamless rest is a small rehearsal of the universe's end, a quiet balancing, a temporary return to stillness. And each morning, when you wake, you begin the cycle again. So perhaps we need not fear the universe's cooling. It is only nature's way of remembering itself. In its stillness, it will contain everything it ever was, every dawn, every colour, every heartbeat, preserved in perfect balance. And maybe, somewhere beyond our physics, beyond the reach of light or thought, the universe will begin again. Not as a rebirth, but as a continuation of the same story, written in a different form. Just as ashes enrich soil, and soil gives rise to new forests, perhaps the silence that follows the last light will become the seed of another beginning. The end of time, then, is not a wall. It's a horizon. Beyond it we cannot see, but that doesn't mean there's nothing there. The universe, like a great breath, may pause only long enough to remember how it began before it begins again. If the universe could dream, this would be its final one. A dream of stillness, not of nothingness. A dream without change, without before or after, where everything that ever was rests together in quiet harmony. The last light has gone, the last motion faded, and what remains is not emptiness but balance. It is as though the universe has exhaled for the final time and found peace in its own silence. And perhaps this is what space and time were always meant to become. Not things, not objects, but relationships. Threads of connection stretched between events, notes in a song that required both sound and pause to be heard. The physicists' equations once described these threads in symbols, but beyond the mathematics they tell a simple story, that everything exists because it relates to something else. Take away those relationships, and reality itself becomes undefined. Time needs change, space needs distance. Without them, the words lose their meaning. Maybe that's why the end of time feels so difficult to picture. We're creatures of contrast, living on differences, light and shadow, motion and stillness, memory and forgetting. To imagine a state beyond those opposites is to imagine a kind of wholeness our minds weren't built to hold. But still, we try. Because even if time one day fades from the universe, it will never fade from us. Not completely. In a way, you carry your own piece of space-time within you. The rhythm of your pulse is the ticking of your private clock, your heartbeat counting the seconds of your personal universe. The space you occupy, the warmth you feel, the air that moves around you, all of it is the local geometry of existence, shaped by your presence. Every breath you take, every thought you think leaves a ripple in the fabric, small but real. You're not outside of time and space, you're one of their expressions. Close your eyes for a moment. Feel the subtle pressure of your body against whatever holds you. The floor, the chair, the bed. That contact is gravity speaking to you. The molecules in your hand attract those in the earth, a whisper of Einstein's geometry. You're held by space-time itself, and as you breathe, the air that enters you is older than memory. Some of its atoms were once part of stars that burned before the earth existed. Some will drift through you tonight and someday rejoin the atmosphere, the ocean, or another living thing. This is what it means to be part of a universe where time and space are relationships. You're connected to everything that was and everything that will be. You're not moving through space-time, you are space-time, folded briefly into the shape of a person. When you smile, the geometry of the cosmos smiles with you. When you rest, it rests. And perhaps when time itself reaches its still point, the universe will do what you do each night. It will sleep. Not as an ending, but as renewal. Just as you close your eyes and allow consciousness to dissolve into darkness, the cosmos may do the same, drifting into a state where nothing happens, yet everything continues to exist as potential. In that deep, perfect stillness, all of its memories, stars, galaxies, living minds, will rest folded together like pages of a book that has told its story well. But before that silence arrives, it's worth remembering that we live in a rare and fleeting moment. The cosmos still burns, the stars still sing, time still flows. Every heartbeat, every conversation, every act of noticing, the sound of rain, the warmth of a friend's hand, the movement of clouds across the moon is a miracle of difference, a defiance of equilibrium. You're alive inside the brief, luminous interval between the universe's first breath and its last sigh. And that makes every second sacred. Perhaps that's what meaning really is. Not a grand design, but the awareness of transience. The knowledge that things change and that within that change we find beauty. If the universe began in chaos and will end in calm, then life is the middle verse, the line that gives rhythm to the poem. As you listen now, you might feel a soft weight behind the words, the realization that the same atoms vibrating in your body once vibrated in stars, and that long after you're gone, they'll continue their quiet work elsewhere. You're made of motion and memory, woven from time itself. And so, when we speak of the end of time, we're really speaking of a change in rhythm, not disappearance. The melody continues. It just shifts into a key we can no longer hear. If the cosmos could whisper one final truth, perhaps it would be this: nothing is ever truly lost. Every photon of light, every vibration of matter, every trace of information is part of an eternal cycle of transformation. Even the silence that follows is not empty. It's the rest between notes, the space that allows the music to exist at all. Without stillness, there can be no sound. Without timelessness, no time. And so, when the universe finally settles into that perfect symmetry, it will not be an erasure, but a completion. All stories will converge, all moments will align. The geometry of existence will close upon itself, and time, the child of motion, will finally come home. Now, return to yourself. Feel your breathing slow and steady. Feel the gentle rhythm of your heart, that quiet metronome keeping pace with the stars. Within you, the laws of physics still hum, the flow of blood, the exchange of energy, the spark of thought. You're a small reflection of the cosmos remembering itself. Perhaps time will end, but the awareness that once experienced it will linger in some form: information, pattern, resonance. The universe began as a vibration, and vibrations never vanish completely. They fade, but their echoes shape what follows. Maybe that is our legacy, to be the echo of awareness in a universe that dreamed itself awake for a while. And as this journey comes to its close, let the thoughts settle gently. Space and time were never separate from you. They were the breath you took, the thought you followed, the love you gave and received. Even when they fade, what they carried remains, woven into the quiet, endless memory of being. So, we have reached the end of tonight's exploration. Whether your eyes are still open or already drifting closed, thank you for joining this quiet voyage through space, through time, and perhaps through yourself. The universe will go on dreaming, and so will you. May your dreams tonight be soft, and may the rhythm of your heartbeat remind you that even in the stillness beyond time, you are part of the infinite,